How about the lamest Super Bowl of all time?
I was so happy.
Rabble, rabble, rabble. All right. So, just for the record, there's no religious comment that like I'm not trying to push or say anything, but regardless of what you believe in, if just the phrase "thank God for something," do you think God really cares about who wins between the Chiefs and the Eagles? I don't know. Maybe. I've never met. Never met. All right.
Okay, I'm not trying to get personal or anything, but like, did you ever mention your personal religious beliefs?
Do you think I have?
Are you comfortable sharing with it?
Would you like me to share?
Yeah.
Not a chance. No way. I'm not going to share my political beliefs. I'm not going to share my religious beliefs. None of that's my place.
Is it confidential?
I mean, I'm sure you could figure it out somehow. Maybe. I don't know. I'm not going to tell you. I don't like, if you guys like me, which I think you do, but you might not. Don't hurt my feelings. I would never want my opinion and your belief on me to sway your beliefs. I want you to come up with your own beliefs. I don't want you to just grab onto your parents or grab onto mine. I want you to develop and critically analyze all of yourselves. Cool. I have never told anybody my political beliefs.
This is a hard no.
I will not tell you my political beliefs. Cool.
Who do you think was going to win the Super Bowl?
That I will tell you. I thought the Chiefs were going to win.
I'm so
Yep,
happy.
I did think the Chiefs were going to win. Anyway, Fred, great question. I don't know, do your other teachers answer those sorts of things?
Yeah, but they don't get too deep. They'll just like do like a thin layer and then.
Yeah. Nope, I do not feel comfortable sharing it. Now, if you guys graduate and we become, like, I don't want to say friends, because that's weird, especially to think about at your age. Although,
Also says the exact same thing.
some of my best friends right now are old students. They have a kid that's the same age as my kid, so we hang out, and it's a very different relationship. However, here,
Wait a minute.
are you trying to figure out who it is?
Yes.
It'd be Jorge Alvarado and Leanne Mears, which I doubt
Pretty
that's
sure he graduated like not too long ago.
18, 17, somewhere in there.
Yeah.
Yeah, so 8 years ago-ish. Anyway, here we are. Today we are going to begin and possibly get through, but time will tell, 7.3, where our focus is going to be around that plasma membrane and a little bit of truth added to it, where our main idea is this thought of what we call cellular transport. Now, in the lab over there, I need a couple days to prep because I thought that, I don't know, I didn't have the realization until last night. I have 3 eggs, and I'll just show you guys. I'm going to pause this real quick. Cellular transport. Okay, I'm going to go grab something out of the lab. If you need to thumb through, we're going to have a bunch of vocab today. So you guys, whether you wrote it down or not, spend just a moment looking at the vocab in 7.3. I got to go grab something from the lab, and we'll talk about what we're going to do with it later this week. So right off the bat, we are going to sneak in our first main idea in 7.3 is a vocab that we're just going to sneak in, and I have a really short definition, but we need to first discuss diffusion. Now, I heard somebody read their definition that they had on their page. What is diffusion?
So, it's substances in water that move in a Brownian motion that causes diffusion.
Okay, do you know what that means?
Partially.
What's Brownian motion?
It's a specific motion where like.
So, and that's fair. As we look at this, anybody else want to try to define it in your own words?
Like a bomb. Like, you know.
So you see the word fuse, I think it's probably.
The passive movement of molecules or like particles from an area of higher concentration to a lower.
Okay, from high concentration to low concentration. Now, as we look at this, we don't have to go crazy into the chemistry stuff, but I'm just going to say that my definition is the overall or the net movement of particles from a high concentration to low concentration. Now, for this, if we need a visual of it, we can get one. It'll be pretty easy to make happen, but I think that we can probably do this without the physical piece. If I have a big beaker full of water, what's up, RJ? Net or overall. So like if you look at a paycheck, do you work?
Yeah.
Okay, your net pay is different than your gross pay.
Yeah.
Gross pay is how much you make overall. Your net pay is how much you actually get money-wise, right? Because what happened to some of your money?
Taxes.
You paid some taxes. So that's all that is.
Oh.
Overall, what actually happens. So,
Pay taxes.
depends if they're legal or not. That's not true. Particles obviously don't pay taxes. Unless we're particles, which we could be. Who knows? I don't know. Anyway, as we're looking at this, we see this happen all the time, and it's really natural. Do you guys have heaters all over your entire house?
Yeah.
Okay, literally every square inch of your wall is heater.
No.
So when you look at this, if I turn, anybody have a wood stove?
Yeah.
Okay, if I have a wood stove and I light it, right, and it's burning, and that's the only heat that I have in my house, does it only heat right in front of the wood stove? Eventually, it will heat the whole house, right?
Yeah.
Now, you guys probably remember some of this from physical science. A lot of that is because of convection currents is what they're called, where high energy, heat, and low energy, they want to balance out. So they're going to mix together till they're all about the same. Now, it's obviously going to be way hotter near the stove, but the heat does go all the way through the whole house. And it's because you have a difference in the densities of those. Hot air is less dense, cold air is more dense. They want to balance so you get them mixing together. Like the particles physically move because the universe wants balance. The same idea happens here with the idea of diffusion. So we have, if I had a jug of water sitting here and I put a drop of red here and a drop of green here, I don't know what color those make. Let's do blue and yellow because that makes green, right?
Yeah.
Let's say I put a blue drop over here and a green drop over here into water, and I don't mix the water. Will they ever mix?
Yeah. Eventually.
How long do you think it'll take? 2 hours? Cool. Remind me at the start of class tomorrow. We'll check it out. Like, we'll have that set up and ready to roll. Cool. So, in this, the same thing that happens, and we'll deal with it, they will mix. And the time question is just kind of an interesting little tidbit. But there's a few things that change this. Now, we are looking specifically with diffusion. We're going to be focusing on in liquids. So there's a reason for that. But a couple things that we need to be mindful of. How fast something diffuses can be impacted pretty wildly by a few different things. What do you think makes it go faster? Hot temperature or low temperature? So impacted by heat certainly does it. Now pressure is another one that is really very common here. When I talk about pressure, what do you guys think of?
Like that it gets tighter.
So I'm fine with that. If we have a bunch of stuff in one little area and on the outside of it there's like no stuff, it's going to move faster to balance out once we pop it, right? So it can be impacted by heat, it can be impacted by pressure, but it can also be impacted by the concentration. So if I have salt water that is like 40% salt and I pour it into some 0% salt, it's going to diffuse and spread out those salt particles way faster than if it were like 1% salt in seawater or fresh water. Okay, so we're just going to say whether it's heat, pressure, or concentration, the follow-up is that higher of any of these means faster diffusion. So higher temperature, diffusion happens faster. Higher pressures, diffusion happens faster. Higher concentrations, diffusion happens how? Faster. Again, some more. Now, here's the part where you're going to feel as though I lied to you, and I kind of did, but hopefully not in a super negative way. Moving forward, within diffusion, a little subsection in here, we're going to talk about facilitated diffusion. Facilitated diffusion. And before you just blindly copy, let me double check this spelling. Yep, just one L. Now, do you guys have any thought that comes to mind when you hear facilitator?
Like transport, almost in a way, because you're like, you know.
Yeah. So one of the big pushes in education, and I know that you guys aren't teachers yet, maybe some of you will be, the old approach to teaching is often referred to as what's called the sage on stage, where I just sit here and I give you fact, right? Like that's a way to do it. I hope that it doesn't always feel like that in here, because facilitating is where we kind of reach these conclusions together, and it should feel more like a discussion. When I see facilitated, I think of teaching, is what I specifically think of. Now, in this, we're going to say that this has a very specific meaning, but I'm going to use a little bit first before I define it. Okay, it turns out that our plasma membrane, remember, it has that phospholipid bilayer. And we talk about the polarity of those phosphate heads and that they kind of tend to repel water, right? Now, there's a lot of molecules in water, and water molecules are really tiny. The real truth of it is they do help to repel some of it, and it helps keeps its rigid structure, but in reality, some water will move in and out of a cell. Okay, it doesn't repel all of it, it's not polarized enough. Some water will move through, and water is actually really, really well able to move through your cell membrane compared to other things. So, little comment here. Some molecules, or ions, if we would rather think of, instead of just being molecules, we can think of specific ions, are small enough to diffuse through the plasma membrane. Okay, some things are small enough that they can diffuse, where they're just going to combine until they're nice and balanced. Some things do that. Okay, oftentimes though, and luckily for us, a lot of the bad stuff or different sorts of elements or molecules that maybe if we have too much of will hurt us, they're not small enough to fit through there. So somebody has to facilitate or assist in them moving in and out of our cell. Hence the facilitated diffusion. We're going to say that this facilitated diffusion, by definition, it's where, what is it that grabs onto something that's outside the cell? The little pokey things that stick out?
Protein transport.
Transport proteins. So check this out. Perfect, nice job. We're going to say that facilitated diffusion is the use of transport proteins and carbs to move things in and out of cells. Now, I'm always going to try to go for the easiest possible, like, I don't want to say oversimplification, but easiest possible version to make sure that we can all click it, and then we'll get more specific as we go. If you want a little picture, we've drawn the cell membrane, and specifically we've drawn the plasma membrane multiple times. Now, we've never done it where we saw specifically these proteins, other than I saw that there were carbs on top. So all I'm going to do here is I'm going to draw one little tiny portion of a plasma membrane. So I'm not going to spend a lot of time. Here's my plasma membrane. Not even going to bother drawing the cholesterol and stuff in there. There's my phospholipid tails that are joining inside outside. I'm good with it. Now, there's a gap between them, right? And it turns out that that gap is necessary, because what we wind up having is, through these carbohydrates and our lovely proteins that grab stuff, we wind up getting these little doors, and much more specific than we were the other day, that actually kind of act like doors. I have a protein, I'm going to bold it, a protein and a carb that work to do something like this. Now, if I have this shape in my hands, could something pass through between my hands right now? What if maybe there's something in my cell that says do this, and they push together? Could something still get through?
Yes.
Where?
Top fingers, like.
So it can get, like, if,
Like bottom and top, because it kind of makes. Like
yeah, so if it comes through here, like, check it out. I have to drop, will you drop this for me? We'll do a drop and it doesn't. Okay, so here's something that my cell wants. Okay, check it out, Jade. He's gonna drop it. Here's my, I'm gonna put it here so everybody can see it. Here's that little door that we just did. Go ahead. Did it get through?
Yeah.
Okay, so that was something my cell wanted. Now let's say that my protein grabs something it didn't want, and all of a sudden this closes. Try it again. Did it get through?
Oh,
So just by changing that, like flexing back and forth, do you agree that it can decide what comes in and out?
Yeah.
It's like my door is open or closed. I heard my stylus fall. There it is. Okay, so with that in mind, that's what we have going on here. We're not going to draw the crazy protein looking at it, but if I have a bunch of little particles floating around, so like maybe here's some water, all these little ones, these little tiny dots are water, H2O. And then maybe we get some little bit bigger ones that are something that my cell needs, like these guys, O2. The water itself, and I know that this goes against what I commented on the other day, but again, whole truth just wasn't quite there yet. This water, does it look like it maybe some of this water particles, because their size, are going to be able to sneak through here possibly? Like they can, they're tiny. Will this oxygen right here, do you think, be able to do the same thing as water? No. So as we're looking at this, what we wind up seeing is that these selective permeability, or these transport proteins and carbs, they can open and close in such a way that things can come in and out. Now, this only works for things that are small enough to fit through there, right? So if I had some big, scary, terrible thing out here, like this big virus, for example, is it possible that that virus fits through that door?
Yeah.
No.
Probably not based on the size, but there must be ways that they do get in, because we all know that we do get viruses and they can make us sick. This idea here, facilitated diffusion, is what helps our cells decide what needs to come in and out. Cool. Now, the nice thing about facilitated diffusion is, do you guys remember talking about the particle model of like matter? What am I? I'm made of little particles, right? We call them atoms, and they have energy, and they are constantly moving. I refer to it as buzzing. They're already moving, which means they have energy. Because all these little particles of water or oxygen, whatever, are actually moving, there's no additional energy needed. All that little particle movement, and I'll write the word additional, no additional energy is needed because all those particles are already moving. They're wiggling around, and they just happen to wiggle right through. That's supposed to say energy, but I'll put the Y back on there. Okay. Do you want an animation of this, or are we cool with the picture? Okay. So now, as we go through here, we had the rule of threes that I discussed last week. 3 minutes without what?
Water, food.
I can go 3 minutes without water. I think you can.
Without air.
3 minutes without air. 3 weeks without what?
Food.
Food. How many for water?
3 days.
3 days. So, when we look at it, do you guys agree with the statement, humans need water? Okay, life needs water, essentially. More than that, cells, which are a part of life, also need water. Everybody in agreement with that? So we need a way to let water in and out of cells in a way that keeps my homeostasis functional. Like, I need my cells to be healthy and happy. So to achieve this, we look at a very specific type of diffusion. Diffusion is just the fact that these particles move and they balance themselves out. With regard to cells, and since we're talking bio stuff, I think green's a natural color, we refer to what is known as osmosis. There's a movie called Osmosis Jones. I never watched it. Maybe you guys didn't either. Nope, Osmosis Jones. It was very similar. I think it was a cartoon based on that. Okay, so osmosis, super easy. We're going to say that this osmosis is the facilitated diffusion of water across the plasma membrane. Now I'm going to use H2O for water across. Does across have 2 C's? No. The plasma membrane. Now, I'm going to take that period away. Facilitated diffusion of H2O across the plasma membrane until, and I'm going to sneak a vocab in here because I think it fits better right here. The universe wants balance. I don't want something to be hot and something to be cold. I want everything to be the same temperature. Your cells want balance. Bless you. If I have a bunch of salt in my surrounding liquid around a cell and no salt inside, there's going to become a bunch of salt that goes inside of my cell, or a bunch of water has to move. In either situation, we are seeing osmosis, where this diffusion, bless you, happens until we reach, or it reaches, a cell reaches rather, what we call dynamic equilibrium. Now, for this is a really fancy looking word, but let's see if we can't pick it apart. When you see equilibrium, what does it make you think of? They're equal. Everybody cool with that? Like they're balanced. Okay? How about dynamic? That's a little bit harder.
Different.
So, good thought. I'll tell you right now, I'm static. I'm being static right now.
Moving.
But now I'm dynamic. I am dynamic as can be, moving. Okay, so as we're looking at dynamic equilibrium, what we wind up seeing is, check this out. I've let this thing run for a few times. Do you think it's about the same red and blue on both sides?
Yeah.
Is it pretty close?
Yeah.
Like, I'm not going to pause and count it, but it's pretty close, yeah? Are things still moving?
Yes.
Even though things are still moving, does it still remain pretty close to balanced?
Yes.
Because everything's moving, right? So sometimes we get some reds that cross over, sometimes we get some blues, but they're all still moving. But I would say they're essentially in equilibrium right now. When we look at dynamic equilibrium, we're just going to say in parentheses, balanced but still moving. Or balanced with movement. Okay. What this means really specifically, and we're going to be talking about concentrations and things like that, there's no change in concentrations. So if no change in concentration, and I'm going to wait to talk more until we're all caught up. Cool. Balanced equilibrium, even though things are moving in and out, we're still balanced. Okay. Looking at this, if you were hypothetically lost at sea and you're super duper thirsty, what's the worst possible thing that a lot of people do?
Drink salt water.
Okay, there's a lot of water in salt water. What happens if you drink a bunch of salt water? You get dehydrated. Why on earth would you possibly get dehydrated? You're drinking a bunch of water. What about it? So you guys, like, you know that it happens, but the actual process to which it happens maybe isn't as easy, right? Just to be clear, the real answer to what happens if you drink a bunch of salt water lost at sea is you get dehydrated and you die. Like, people die from drinking salt water. Yes, sir?
If you boil it, it's safe to drink though.
Nope.
No? It's
Nope.
not safe?
It would actually be less safe if you boiled salt water to drink it.
Oh, because the water get.
Because now you have a higher concentration of salt because the water leaves, but the salt doesn't boil out of it. So now if I had a pound of salt in a gallon of water, now I have a pound of salt in a half a gallon of water, and it's just way higher concentration. So I like your question. If you had salt water and you wanted to make it drinkable, how do you possibly do it? You could filter it. It won't always work. Depends on the type of filter that you have. If you boil the water, does the salt boil too?
Yeah.
The salt stays behind, which means if I boiled it, all that steam is just water now. So if I were to run that steam through a tube and cool it down so that it condensed back into a liquid, that's called a distillery. That's how you get distilled water. I now have pure water, no salt in it.
Also, like, say if you put like a pot and you like, you know how you put fruit into those plastic bags that you would like at the supermarket? I don't know if you guys have
Yes.
those. Yeah, those. Say if you were to like fold it out like an umbrella, the steam comes up and it makes a steam and water starts.
If you collected the steam and the water from the steam, you could drink that. Absolutely. Okay. Which there's a bunch of weird things like survival stuff, and I'm not like your troop leader or nothing for Boy Scouts or anything like that. But do you guys ever watch Bear Grylls' show? So Survivor Man or Man vs. Wild or something? I don't know. He does a bunch of really gross stuff. But one of the things that he demonstrated, like, in a desert environment, one, if you're in a desert and there's no water, what are you going to be tempted to drink? Like, honestly, it's going to be pee, right? Like, as long as you're peeing, you're going to be tempted to drink it, especially if you're, like, really dying of thirst. However, remember, we haven't gone into this, but pee is all the waste from the liquid that your body doesn't need. Like it goes through your kidneys, say kidneys, nope, get out of here, we don't want it, and then you pee all the bad stuff out. So if you drink your pee, you're literally just putting all that bad stuff that your body got rid of back into your body, and it's not going to work, right? However, is there a lot of water in pee?
Yes.
There's other stuff that's not good, but there's water. So similar technique with that plastic bag that you were talking about. You pee in a hole and let the heat and the sun start to evaporate it. Water is going to taste terrible and pool on the underside of that bag, but you can get fresh water out of urine.
You just dig a hole.
For real, you dig a hole, you pee in it, and then you cover it so that the condensation is water. Yep. It's gross, but the alternative is you die drinking your own urine. So I'd probably rather take the second. So here we go. As we're looking at osmosis, we get some fancy sounding words here. Real quickly, we need to make sure that we understand this idea of concentration. So entirely up to you whether you put this one or not, but let's think about concentrations. Now, do you guys remember doing mixture problems? Like, I have 50 milliliters of a 37% solution. How much of a 50% solution do I need to add to get a 40%? Do you guys remember problems like that?
I think.
Like, you've seen them. I guarantee you've seen them. If you need the review on concentrations, I would include it. If you think you're good, I'm not going to destroy you if you don't have it in your notes. But I want to make sure that you're listening. So, let's think about a concentration of stuff. And let's use salt water. That's an easy one to think of. So I'm going to draw one square, and I'm going to fill it with water, which I'll just make as blue. So here's a blue square. Hopefully we'll see if it works. Cha. And then I'm just going to copy this. So I'm going to have 2. Okay. 2 squares. Cool. Let's say that this first one, and these are not realistic numbers, but we're just using it to make sense of. Let's say this first one has 1, 2, 3, 4, 5, 6 little white specks of salt in it. Okay. Now, I don't have the actual water in here, but we'll make up nice numbers. And then this one has 3 little specks. So I'm going to say same amount of water in each. Is it the same amount of salt in each, though?
No.
Which one's a higher concentration?
The one in the middle.
Okay, so I don't know the actual number, right? But let's say there's 1,000,000 or 1,000 particles of water. In this, the concentration we could say is 6. We'll get there. We could say this has 6 salt per 1,000 water. Okay, this one over here has 3 salt per 1,000 water. And these aren't realistic numbers, it's just to make sense of stuff. Okay, which one's a higher concentration? The left. It's twice as strong, right? So, you do not have to draw this next part, but hypothetically, let's say I connected these 2 things with a tube, and we'll do it at the bottom so that it could actually flow nicely. Let's say I connected these 2 with a tube, and I opened it so that water could flow through. What would happen? They would balance, right? It would be 5 and 4 or 4 and 5, which is a weird because the even part, right? Bam, bam. But the salt would balance itself out between these 2 things. That is essentially diffusion, that balancing. Now, if we were to look at osmosis, instead of having a tube here, it's just simply the plasma membrane. Cool. Everybody cool with concentration, at least basics? Yeah. Sweet. So, as we go through here, additional review we don't need to write down, but I am going to talk about. We see that I have a difference in concentrations here. I'm fine with that. And I want balance between them. I had a bigger point to make, but I lost it. What's a solution? So you have a solvent and a solute. Which one's a solute and which one's a solvent in this example?
Solvent would be like fluid.
So I like that you're thinking. I don't necessarily like your answer, but I'll tell you if you change one little thing, you're going to get it. The solute is the salt, the thing that we're dissolving into it. What's the solvent in this case? Water. Okay, so a little bit of review stuff there. We have concentrations, we have solutes, we have solvents. Now, hypothetically, if these two were already balanced, and I'm going to draw pictures for each of these, but we're going to get some fancy words. Right off the bat, first one, and I think we had a bullet point, right? Osmosis. Cool. So we get what is known as an isotonic solution. Okay. This word, iso, tells us everything that we need to know, and you guys might not have seen it. In math, oftentimes, is where I think of math 100% when I see the word iso. You guys probably have, ooh, I like that. I did not think of that word, but absolutely. What's an isosceles triangle? Isosceles. What are equal?
Wait, what do you mean?
What's on an isosceles triangle? Something's equal.
The angle.
The base angles, but also two sides, at least two sides. So when you see iso, I love that idea of equal. I think of the word isometries, which are congruence transformations. I think that word shows up, but I'm just going to say, hey, this is Greek for equal. Now, when we're looking at these solutions, we're going to see three of them, just so you guys know. The isotonic solution means stuff is equal. Specifically, we're going to define it, and then I'm going to leave a little space over here to draw a small picture if we need it. When the concentration of liquid, and normally it's water, but liquid outside the cell so I have a cell that most of them live in watery environments. If I have the water that they're living in and the concentration of all the stuff outside the cell is isotonic, we'd say it's the same as inside the cell. Iso meaning equal. So when the concentration liquid outside of a cell equals the concentration, and I'm going to use CONC if that's okay with you guys. I lied, you should, but I'll write it. And I'm going to put this in quotations, liquid inside cell. Now, if they're equal, do we have to have any movement happening? If they're already balanced, do we have to do anything else to balance? Okay, no, says RJ. These are already balanced, but they're still moving, right? Because particles constantly move. The same thing happens with our cells. So as we look at this, liquid inside the cell, this, we're going to get this word, I'm sure we'll see it again. It's more like a gel, just so you guys know. But this is referred to as a cytoplasm. That liquid inside the cell, that gunk where all of our organelles live, it's referred to as a cytoplasm. Okay, when the concentration is the same inside and outside, nothing has to change. So this is nice and balanced. For this, these commonly have a few different things that we're going to look at. What might a cell need inside? Like, we use sugar to make energy, right? Carbohydrates and our saccharides is how we get energy. Sugars need to move in and out of your cell then. Sugars have to do this. Anything else? So sugars, good. Oxygen. Proteins, commonly, if they're small enough at least. And then other nutrients, blah, 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 dot, dot, dot. Most of the cells that we deal with are in an isotonic solution. So for example, blood cells live in the liquid that makes up your blood, right? So there's little red blood cells in there. They're already balanced. They don't have to take stuff out of your blood and in. Most of the time it's nice and balanced. Most cells are in this. Now, nothing has to change. I'm not going to draw a picture here. Isotonic is the same. Cool. Anybody recall the second type that we might look at from the vocab that you just looked at ahead? There's two words. If somebody's hyper, what does that mean? A lot of energy. What if somebody's hypo? You don't hear that one as often.
Low energy.
Low energy. Okay, so 2 additional situations that we'll look at. First is hypotonic solution. And when I think of this, hypoglycemia is something that I think of. You guys ever not eaten and you feel weak and shaky and stuff? Okay, what you're feeling is hypoglycemia. Glycemia from sugar, glucose and glycogen and those things. Emia presence in blood. So low sugar levels in your blood is what hypoglycemia is. Which means when you see hypo here, low or high? Low or under, whichever one that makes more sense to you. So, as we're looking at these, it is easy to get goofed up, and I get goofed up with them as well, but we are looking compared to the cell. So if we're in a hypotonic solution, we just have to say concentrations outside of the cell. Concentrations outside of cell. Are lower. Okay, there's an immediate thing that winds up happening, and we're going to draw a little tiny picture to try to make this make sense. So we're going to look at a little sliver here, and I'm going to have you guys, we'll all have the same initial picture, and then I'm going to ask for you to try to do the additional part. Let's say that I am looking at a cell, and then here's my plasma membrane. And your plasma membrane doesn't have to be perfect. I'm just going to draw it like this. Okay. Let's say that this is in and this is out. So everything over here is inside of my cell on the right side. First thing that I want you to do is we'll just use dots. We'll just assume that there's the same amount of water. Like the water's been diffused. It's nice and easy. If I want this to be the inside of the cell has a higher concentration. Oh, that's the first time I've coughed today. Concentration outside is lower. I'm just going to use little black dots. So let's say here's a bunch of things inside my cell, and I've counted 7.
Do we draw that?
I would. Okay. Inside the concentration is 7, whatever, right? If I want a hypotonic solution, should the outside be more or less? Less. So check it out. We have these. I'm going to make them kind of bigger, and I'm doing this for a reason. Okay. So I see that my cell has way more stuff in it than the outside surrounding environment. Everybody cool with that? All right. My cells love the fact that the concentrations are different, or they hate it? Which one? Because you gave me both.
Hate it.
They hate it because they want balance. We always want balance. So if this is where we're at, we need to get balance somehow, right? Now, there's 2 ways that you can do this. Either one, you trust that all of the proteins, all of our carriers, are going to take the exact number of stuff and move it to the outside instead. That's one option. Or, what's easier than having to necessarily carry these things back and forth? What is able to pass through this membrane pretty easily? Water. Instead of moving that out there, could we change the concentration by taking water inside or outside of our cell? Okay, so from this picture, what you're going to do is you're going to have to adjust the amount of water that's inside or outside of your cell. Okay, using this idea, here's the same cell picture that we have, and I'm just going to really roughly, I'm just going to do this as bigger one. I'm not going to draw my membrane yet. If I want the concentration to balance, what do I have to have more of in my cell? I have to have more water. So to do that, if we look at the same picture, do you agree that to have more water in it, the cell must have grown? Like it must have a larger size to hold more water, right? So at this point, I know it doesn't look like it, but if I still have 3 of these particles outside in the same 1, 2, 3, 4, 5, 6, 7 inside, is it possible that the concentrations are now equal? What do you think? Talk it out. My question is, by adding more water inside of my cell, does that change concentration? What we're seeing, we need more water, H2O, in cell. Okay, because it wants to balance. I can add more liquid to lower the concentration. When I do this, there are some huge impacts on cells. If you have some cell that's just kind of hanging out and it's nice and flexible, and I'm trying to think how to make that super clear. The outside membrane can stretch and stuff. Okay, if I add more water, does the cell have to get bigger? It would have to, right? Now, plants do this constantly, and that's really good that plants do it. You ever seen a plant looking really sad? It's because there's not enough water inside of each of the cells, so when you water it, more water goes in and it perks up. This thing has huge, or this idea where we see this concentration changing. We're going to say movement of water, movement of H2O into cell. It doesn't make the cell bigger or smaller again. If you have a balloon and you add more water, what happens to the balloon? Makes it bigger. Now, and I'm going to say makes it swell specifically. Now, in plant cells, that's awesome because they don't have a rigid membrane outside to like hold it solid. If you did this to something that wasn't stretchy like a plant cell, like, I don't know, a human cell, what do you think might happen? Pop? Like, it's going to literally destroy it. Now, super simplified again, but how many of you guys drink water every day? Obviously, like, how much water do you drink a day?
Like 8 cups, for example.
So that's the good standard amount. A better amount is 1 ounce. Like, take your body weight in pounds, divide it by 2, and that's how many ounces you should drink, roughly. Okay. With that in mind, what happens if I'm feeling crazy and I just chug like 2 gallons of water right now?
You might like pop, like.
I very likely will die, just so you know. Like, maybe my gut will pop because I drink it too fast, but on the cellular level, water intoxication and overdose does happen. Happens with dogs when they play in pools and go crazy with it. If I lower the concentration of all my blood due to all that extra water, that water is going to rush into my cells. My animal cells inside of me can't get bigger. They have a firm membrane around them and it'll start to pop, and all of a sudden all my cells start to kind of destroy themselves because of this pressure difference, and I die.
Oh, so they don't pop, because I know some people said like it just fills your lungs and you just like kind of drown yourself.
So, but check it out. Your cells are made of lungs, right? And if they have too much water and then they pop, all that water goes out, and now you're drowning in your lungs because all that water is out of your cells. Like, that is what's happening. Okay, your homework for tonight is one more. We have hypotonic, which means the concentrations outside are low. The last one, I want you guys to finish this and draw me a similar picture. Is as compared with hypo, we get hypertonic. Solution. I want you guys, for your assignment tonight, at the start of class tomorrow, I'm going to check it. Hyper is the exact opposite of hypo. Hyper meaning what then? High or above, right?
Yeah.
So outside of the cell, we have a higher concentration of stuff. Okay, your job is to define that for me, and then I want you to do the same thing that we did here with a simple picture, except this time outside of our cell has way more concentration. So here's my membrane, and dun 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 dun. Cool. Same thing. I want you to tell me what has to happen with the water to fix this balance. All right, later, Raiders. This is your homework. Bring it done tomorrow. Finish the picture.